Good evening, everyone. I hope this finds you doing well. First of all, I want to say that I'm very proud of what you guys have been doing here in this chapter 15. It's been a very difficult chapter, bringing all the things that we've learned all year long back into this curriculum. So this last section, though, you're going to find is pretty simple. We are going to be talking about boiling point and freezing point, both things that you've had some experience with in the past. And so the first thing we're going to talk about is a colligative property. And again, this is something that you have done a lot with. It says properties of solutions that depend only on the number of dissolved particles. And we're going to use molality instead of molarity. Okay, so the first part about a colligative property is that it is saying it only depends on the number of dissolved particles. And you guys can witness this every time you go by Koch Refinery and you see all the smoke that's going up into the air. We don't really care what the particulates are. I mean, we do from a health standard, but in terms from the colligative property, we are only worried about the number of dissolved particles that you are seeing. The more dissolved particles you see, the smoke, the fog, the pollution, that's what you're seeing going into the air. And so a colligative property, the reason we're going to use molality instead of molarity is because molarity is temperature dependent. So if you recall, molarity is the big capital N that we've been using is the moles of solute, so it's the stuff that's being dissolved, over liters of solution. And remember that these liters of solution have two parts, the solute plus the solvent. And the one thing that I don't think that I've been stressing too much about molarity is that it does depend on temperature. And so molality does not. So again, we do not care about the type, how many, we do care about how many, but we don't care about the identity of the particles, and we don't care about the temperature. And that's why molarity is sometimes useful. Molality, excuse me. And so we have molality is going to be a script letter M. So it's just italicized. It is the number of moles of solute, so that's the stuff being dissolved, per kilogram of solvent. And so you can see the formula here. It's pretty simple, just like molarity is. And this is also going to be on your gold sheet that you're going to be able to use so you know what the formula is. So it measures the ratio of the particles to the solvent particles and does not vary with temperature. So let's put this into use. What does this really mean and why are we going to use it? So the first thing that we're taking a look at is vapor pressure lowering. And so if we have a closed system, and I know I don't have a closed system here, but let's imagine that it is, a non-volatile solid always lowers the vapor pressure. So if you can think about that, these particles inside here, inside this, let's see, where am I at over here? The particles inside of here, they want to gain some energy and they want to be able to escape. But even as I'm drawing this, you guys can see that there's particles in my way. So because the particles are in my way, it's going to take a whole lot more energy down here to get that particle to get out into the vapor phase. So the degrees in vapor pressure is proportional to the number of particles that are in solution. So if I add some more particles, there's more things in the way, and it's going to take longer for these particles to get out of the liquid phase. And you can see down below here at your notes that you have, we have 1 mole of sugar. It's 1 mole of particles. I have NaCl, which is plain old table salt. We've been looking at this all year long, that it's going to dissociate into sodium and chloride ions. It has 2 moles of particles. Now in my solution up here, I don't care that it's Na and Cl or sugar or whatever it is. I just got particles in my way, and I'm not going to be able to gain enough energy to get from a liquid to a gas very easily. And then you can see with calcium chloride, it has 1 calcium for 2 chlorine, so I have a total of 3 moles of particles in my solution. All right, boiling point elevation, so it does the same thing. We're not going to talk too much about this. The boiling point elevation isn't as greatly affected as it is by the freezing point. You'll see that in just a second. So you can see down here, we know that the boiling point of water is 100 degrees Celsius. And when I add some particles, it's going to raise it to 102.5 or up to 105 degrees. Now you might be thinking that you're making some macaroni and cheese and you're putting that pan of water on the stove, a very good dryer here, and you have water in here, and you might go ahead and add some salt in here for some flavoring. So is it raising the boiling point? In theory, yes, but you're adding very few particles as compared to the amount of water that you probably have in the pan. So it might be raising it at 0.05 degrees or something like that. It's very, very small. So boiling point elevation does play a part, doesn't raise it as much as lowering it. So the freezing point depression is what we are going to be talking about in class tomorrow. We are going to be taking and doing a lab, and we're going to figure out the freezing point of BHT, and then what happens when we add a solvent to it. And so we're going to take our freezing point depression and we're going to determine it from the pure solvent. So we've done this lab part of it one way already, and now we're going to add something that's going to lower the freezing point because you're going to have particles that are getting in the way. So they disrupt the orderly pattern. And if you can think of freezing, again, we are going to be taking something that is from the liquid phase, getting down into the solid phase. And we know that solid particles, when they're solid, they want to be side by side by side, very, very close to each other like this. So I'm trying to draw them here. And in the liquid phase, they're a little bit further apart. Well, if they're trying to come closer and closer and closer together so they can freeze, what's going to happen if I input another particle in the way? It's going to take longer for it to get down and lose its energy to be able to change its phase. So again, it's proportional to the number of particles that you have in solution. And you can see that I have molality of glucose, some salts, some aluminum chloride, and how much it is lowering it. And so this plays a huge part on our roads here in Minnesota. If you think of the highway, all right, you think of the highway, and what they're going to do is they figured out now that it's better to pre-treat the roads, meaning that they're going to put their salt solution, the salts, down on the roads first, and then when we have some sort of storm coming in and we have these snowflakes coming down, what's going to happen is that these particles are going to get in the way, so this snow that's coming down is not going to be able to freeze as easily. It's going to take more energy to do that, to get to the road and freeze on the road. And so they figured out that by putting these particles down first, it actually slows down the freezing process. Years ago, when I was learning to drive, they didn't treat the roads until after there was already ice on the road. And so it took a lot longer, it wasn't as effective as it is now to have those salt particles on the road first. Now, obviously, they have to have some sort of density to them so they stay on the road, and that's the risk that you take. You can't treat it too far in advance to be effective. So I want you guys to draw this graph because this is what we're going to be doing here in class. So I want you to go ahead and draw an XY axis. Let's see, where am I at here? It's been a long time since I have recorded at home, which is what I'm doing. I've been using my smartboard at school, but today I happen to be at home. All right, so here we're going to say that we have degrees Celsius on this side, and we have our time over here. So we have already done this once, where you guys took some BHT and you heated it up to 90 degrees, and you saw that it came like this, and then we were looking for that plateau. And this was in chapter 14, and we figured out that that plateau is going to be where our BHT freezing point is. Okay, so now what we're going to do this time is we are going to take some BHT and we're going to add a solute to it, PDCB, pyridichlorobenzene, and that's going to get in the way of the freezing. So it's going to come down like this, and we're going to cool it and cool it and cool it. It's not going to have a nice plateau like we saw here with the BHT. So this is going to have BHT in it plus a solute. And what you are going to find is that the freezing point has been lowered. We're going to draw similar lines where we have this decreasing, something like that. And then we have this line, best fit line here. And so this is going to be the freezing point now of the BHT in the solute. So what happened is this solute got in the way of the BHT nice freezing that happened when it was just there by itself. There wasn't anything in the way, so we got a nice plateau. And now if you remember those particles, oops, I'm that far apart, the particles are in there. There's my BHT, and now I am adding my solute to it, put those in X's, and as we talked about already, these are getting in the way of the BHT particles getting side by side by side as they cool. And so the result of that is you get this slope of line that is not as nice as it is with the plain solute. Okay, so when we take a look at this then, we have our, what we call this in between here and here, is going to be our change in our freezing point. So we write down change with our delta, T, and F, and this is going to be our change in our freezing point for the BHT. And you would just subtract those two numbers there, and that would give us our freezing point. And so what we're going to do is we're going to try to find our freezing point constant. So we use K for a constant, F for freezing point, and then that is going to be equal to our change in our temperature of our freezing point divided by our molality. And so again, this is going to be representative of how many particles of the solute did we add. And then this would be the constant of how low BHT is able to go. Okay, so that's about it. This is what you need to know for our lab the following day. I hope you have a wonderful night, and I'll see you soon. Take care.